So hello everybody, welcome to this important series of constraint motion. So we are dealing with the fifth problem in the constraint motion series, and in this fifth problem this is the diagrammatic setup which is given to us, where this free end is given a velocity u, and if at an instant of time the string is making an angle theta with the vertical, then we need to calculate the velocity v with which this block is moving on the horizontal surface. So in order to solve this using conventional approach, this is the diagram which we have. So if at an instant of time we consider something during the entire range of time, so the separation between the fixed support and the horizontal floor, that is distance d, remains constant throughout the motion of this block. And this part of the string, when pulled in the downward direction, will eventually drag the block in the forward direction. So if at an instant of time we consider that this separation is y and this distance is x, so we can be certain about one thing, that the total length of the string is constant. So total length of the string is going to be constant, and if we calculate the total length of the string, so this length of the string will certainly become from this triangle y and d, that is root under y square plus d square, and followed by this we have a distance x. So this entire length of the string is constant. So for this string we can also say that the velocity v is because of change in y, that is dy by dt in magnitude, and the velocity u is because of the change in x, that is dx by dt in magnitude. So now if we differentiate this expression with respect to time, so differentiating with respect to time, so if we differentiate this expression with respect to time, then we write it as 1 by 2 times of root under y square plus d square times 2y dy by dt plus dx by dt, and derivative of constant is 0. So over here we can cancel this 2 out, and then we can write it as y upon root under of y square plus d square, dy by dt can be written as magnitude of v, dx by dt can be written as magnitude of u, and this is equal to 0. So over here we can say that the distance y and this distance root under y square plus d square, so this expression will take the form, so sin theta can be written as perpendicular by hypotenuse, so we can put this as sin theta. So we can say v times sin theta plus u is equal to 0, and therefore v can be written as minus u by sin theta, and in terms of magnitude we can simply write v is equal to magnitude of u cosec theta. So this is the answer to the problem which we have solved. Now if we solve this using another approach, that is method 2, which I say that the total work done by the tensional force or the internal forces involved is 0. Again I would like to mention, if you have not seen problem 2 where I have discussed this entire method, why we are using this, you can go back and watch problem 2 of the series. So over here we can say that if tension T is the tension in the thread, and if at an instant of time this is moving with a speed u and this one is moving with a velocity v, then it is making an angle 90 minus theta with the t vector. So over here if we write the expression, so we can say that t v cos of 90 minus theta, so we are technically doing dot product of tension and velocity vector, and at this point we can say minus tu, and this is equal to 0 because net work done by internal forces is equal to 0, and therefore we can say tv cos 90 minus theta as sin theta is equal to tu, and from here we can write v is equal to u by sin theta, or simply that magnitude of v is equal to u cosec theta. So much faster, always the preferred way of solving this kind of a problem. But we discussed the conventional ones for you to understand the mathematics behind the entire aspect, mathematics to understand how constraint motion really works. So I hope you are liking this series. Continue to watch the channel. Please like, share and subscribe. We will move on to the sixth problem to understand more about constraint motion.